Hey everyone, welcome back to Chem Story. Today we're going to dive into another key reaction, intermediate in organic chemistry, carbenes. These guys show up in all sorts of reactions. And to really understand how mechanisms work, you've got to know how carbenes are structured, how stable they are, and how they react. So let's walk through it step by step and break it all down together. So what exactly is a carbene? It's a superreactive intermediate, where the carbon forms just two bonds and holds a lone pair, making it divalent. Now, unlike your typical carbon that follows the octet rule and has 4 bonds, a carbene only has 6 valence electrons, so it's short 2 electrons. And that's what makes it so reactive. Even though it's missing electrons, a carbene is still neutral, no formal charge. But here's where it gets interesting. Carbenes can exist in 2 different electronic states, singlet or triplet. Singlet carbenes usually behave like electrophiles, while triplet carbenes act more like radicals. These two have very different electronic structures, geometries, and levels of stability, and those differences have a big impact on how they react. And because they can flip between these 2 states, carbenes take part in all kinds of reactions, like cyclopropanation, insertion, and rearrangement. That's why they're such an important player in organic chemistry. So let's take a closer look at each one. Let's start with singlet carbenes. In this case, the carbon is sp2 hybridized, and the lone pair sits in one of the sp2 orbitals. There's also an unhybridized p orbital, usually empty, but it can sometimes accept electrons from nearby groups. Because of this setup, the geometry ends up being bent, not linear, with bond angles around 100 to 110 degrees. Now here's the catch. In singlet carbenes, both non-bonding electrons are sitting in the same orbital. That causes a lot of electron repulsion, which pushes the energy up. So singlet carbenes are usually higher in energy than triplets. But if there's an electron donating group nearby, that group can help stabilize the carbene. It can donate electron density into that empty p orbital, kind of like filling the gap. And if that stabilization is strong enough, a singlet carbene can even exist as a ground state species. Now let's move on to triplet carbenes. Most of the time, they're also sp2 hybridized, but in some rare cases, they can be sp hybridized too, though that's not common. In a triplet carbene, the 2 non-bonding electrons are in separate orbitals, one in an sp2 orbital and the other in a p orbital. Because the electrons are spread out, there's less repulsion, and that's what makes triplets more stable than singlets. For many simple carbenes, especially ones without stabilizing groups, the triplet state is the default. But if you have resonance or electron-donating substituents, the singlet state can actually become more favorable. So the reactivity of a carbene really depends on whether it's in the singlet or triplet state. Singlet carbenes tend to act like electrophiles because of that empty p orbital. But if there's an electron-donating group nearby, that group can stabilize the singlet. And that reduces how electrophilic it is, because it fills in that empty space a bit. On the other hand, triplet carbenes behave more like radicals. They're good at homolytic reactions, splitting bonds evenly. And their stability can also be influenced by the substituents. Bulky groups, for example, can give them a bit of steric protection, which slows down their reactivity. Now that we've seen what affects stability, let's move on to how carbenes are actually made. One common way to make carbenes is through alpha elimination of a haloform, like CHCl3, with a strong base. For example, chloroform reacts with hydroxide. The base pulls off a proton, and that gives you a carbanion. That carbanion then kicks out a chloride ion, and boom, you get dichlorocarbene. This carbene is super reactive, and it's often used in cyclopropanation reactions. Another method is photolysis of diazomethane. When exposed to UV light or heat, diazomethane breaks down, releasing nitrogen gas, N2, and forming methylene carbene. Methylene reacts a lot like dihalocarbenes. It can insert into bonds or react with alkenes to form cyclopropane rings. So these are 2 major ways we generate carbenes, and they explain why carbenes are such a big deal in synthesis. Understanding these reactions helps us predict how carbenes will behave when we use them in different transformations. Alright, that's it for today's lesson. I hope this breakdown helped you get a better handle on carbenes and how they work in organic chemistry. Thanks for watching, and I'll see you next time.